Okay, welcome, all of you, Tandia and Tia Betsy and Esther and Charles and Bailey and Juliana and Constance. Welcome to, this is the week 5 webinar. And what we're going to be talking about today is actually really important. And it's going to be the rest of the course. And that is the central limit theorem. In fact, without the central limit theorem, we wouldn't even have this class, because you couldn't do anything from now on. So everything we do from now on is going to be using what we're doing today. And I am going to talk about some of those uses. And I'm also going to tell you the central limit theorem. And that's a plan. One good news for you guys, is that unlike last week, there's no major pieces that come this week. Last week we had 2 big things. We had the project and you had your online exam. This week is just a regular old week. Most weeks are regular week, but this week's a regular old week. So what we're going to do is we're going to look at just chapter 7. I want to mention a few things. One is that I am a little more than halfway through grading your projects. They take a long time. It's hundreds of pages of reading to do for me, because there's a lot of you and projects are long and I have to read through and write comments and stuff. What I do is I only grade 1 per group and everyone gets the same grade. And the suggestion was only 1 per group submit. But if more than 1 submits, then I basically just take the first one that comes up on my list when I click. So, and then I grade that and give everyone the grade. So that's just a note. And so if you're especially if you're the one that I graded and wrote comments on your paper, make sure you share with your partner the comments that I wrote, because those comments and your paper itself don't get shared with your partners. So I'm going to let you do that to share with your partners. Another note is that for project 2, you don't have to have the same partners, but you can. It's up to you. So I still strongly recommend 3 in a partnership, but you can switch around if you want, and that could be fine. Make sure that if you are leaving your partners, to let them know so that they have an idea of what to expect. So that's kind of you have a long time for the project, but I figure I should mention that part of it. We're not even ready to think about the content of it yet, because we haven't learned about it yet. That's another week or 2 or 3, and then we'll talk about it. Next week I'll talk a little bit about it. The week after I'll talk more, and then the week after that we'll finish off the talk on it, is the plan. And today is just partner time. Okay, so that is the plan of the day and what's coming up. So let me ask you, are there any questions for any of y'all? Any questions before I move to what we're going to talk about today? No questions? Okay, I thought we would go to, I'm going to show you a news article. One of my favorite thing about this class is it's pretty easy to go and search, find some kind of thing that's happening in the news, something that's important, and look at statistics and see how it used statistics. And in particular, the main thing that this class deals with are surveys. And the central limit theorem is a huge piece of understanding the power of a survey. So I'm going to share my desktop. And I just grabbed this from the news. Just 1 second, I want to make sure I have the chat in there. Okay, and again, feel free to ask questions as you get them. Okay, so this is a news article, and hopefully you can all see this. And they did a survey, and they said 1 in 5 passengers say they'll never feel comfortable flying on a Boeing 737 MAX. Okay, I'm not sure if you followed the news. Have you guys all followed that news? Anyone know what happened? Yeah, so what happened? Yeah, they crashed. Okay, and the question is it that all Boeing 737s are like horrible and you should never fly it? Maybe they're going to fix it. That's not statistics, that's engineering. What we're going to be looking at is how people feel about it. So one thing is, do we know that 1 in 5 people in, say, the whole world, in fact, let's talk about what we have. Okay, so what it says in the wake of 2 deadly crashes, it's not just it, actually, it's they crashed. So there were 2 crashes. Boeing has said it's making progress, okay, on efforts to get its grounded 737 back to fly again. Okay, then we got to make sure, then they have to make sure that passengers get back on board. Okay, so then it says a new survey by the Barclays Investment Bank. It's interesting, I didn't know Barclays Investment Bank did surveys, but they did. Suggests that they have some work to do. Okay, so in particular, the survey included 1,756 people in North America and Europe who said they typically fly at least once a year. So let me ask you something. They found that 1 in 5, let me go back to the main thing, 1 in 5 say they'll never feel comfortable flying on it. All right, so the question is, do you think that is a good representation? And can we say that 1 in 5, which is 20%, by the way, can we say that 20% of all people in North America and Europe never want to fly in one of those planes again? Okay, or never feel comfortable flying in those planes. What do you think? You think that's a reasonable thing to say? That 20% of all people in North America and Europe feel that they never want to fly. Okay, they'll never feel comfortable flying in those planes. What do y'all think? So you can say it or put it in the chat box. So do you think it's reasonable to say that 20% of all North American and Europeans will never feel comfortable again? So I don't see y'all responding. Let's see if you can respond and tell me how you feel. Okay, so you're saying no and no. Okay. All right, so the answer is they did a survey. They did a survey of 1,756 people. And I think you know there's a lot more than 1,756 people in North America and Europe. Okay, if you don't know that, then I don't know where you've been, but you should know that. So the question is, what can we say? Because they just did the survey, a very, very, very small percent of all North American and European people. So is it reliable to say that 20%? Do you think it could be 80%? Okay, in other words, how reliable do you think it might be? So any thoughts on that? So do you think it's just nonsense and they have no idea? Or do you think they're like know within 0.5%? They know within 5%, 20%? What do you think? What's your guess? What's your guess on kind of how much they know it by based on this survey? And you can all guess. By the way, I won't take off points if you guess wrong, but I won't be happy if you don't say anything. Okay, so 5 and 80, very different, by the way. Bailey and Zach have very different guesses, which is fine. But we're going to be talking about that. Okay, so how do we find out? Now, the way we find out is we think about the standard deviation. Okay, and we got to think about what I mean by the standard deviation. So we want to look at surveys. When you talk about how reliable it is, we can think of these survey groups as they're in the business of collecting surveys. And let's suppose that we looked at a lot of different surveys of 1,756 people, and let's say they were randomly selected. Then the question is, how much will the surveys vary, the survey results, which is a proportion of people who will never feel comfortable on that plane. Okay, so how much do the surveys tend to vary from the true population proportion, which we'll never find out what the true population proportion is, but we can talk about how much they'll vary. Any questions on that idea? And how much something varies is standard deviation. Okay, so now comes a big theorem. So I'm going to go and, oh, you know, I didn't set this up, so let me set this up while I talk. So the idea is we need to have a theorem that tells us how much a survey is likely to be off from the population mean. In other words, if you look at all, if sample survey means or proportions in this case, how much are they going to fluctuate from one to another, or what's the standard deviation of all possible sample proportions with that sample size? So who's lost on what I just said? Anyone lost? Maybe I should have said who understands what I just said. Just what the question is. I haven't even given an answer, but any questions on it? Okay, so we can think about taking surveys. So we took a survey of 1,700 and some number of people, or they did, and they're going to get a sample proportion. Well, if they picked a different group of people with the same sample size, they'll get a different sample proportion. Do y'all agree? Okay, they're most likely to get a different sample proportion. And they could do that all day long. And each time they're going to get a different sample proportion. We can write down those sample proportions as a big long list of sample proportions, and we can look at that as our new data set. And the question is, what is the standard deviation of that data set? And also, what's the mean of that data set? So notice we started with a yes or no question, but we got a sample proportion, which is a number, and we're looking at all possible sample proportions and saying, is the average of those sample proportions the population proportion? And what is the standard deviation of those sample proportions? Any questions on that idea? And all of the possible sample proportions is called the sampling distribution. So I'm going to reshare my desktop, but now we're going to do it where I can write. And you're used to this. And what I want to do is I want to define some stuff that are really important. I think I'll do it in red because it's that important. Okay, so the collection of all sample proportions with the same sample size is called the sampling distribution. Okay, because we're going to have a distribution of all possible sample proportions. Any questions on that statement right there? Okay, now comes the big theorem. What we want to do is we want to say, oops, one more time. That guy, that guy, that guy. There we are. What we want to do is we want to say, well, what is the mean and what is the standard deviation for this sampling distribution? And this is called the central limit theorem. For proportions. What it says is that the mean of the sampling distribution is the same as a population mean. And by the way, if the mean of the sampling distribution is the same as a population mean, then we call that an unbiased estimator. So the sample proportion is an unbiased estimator for the population proportion. Another way of thinking about that is that if we collect data, you did that big survey, then you look at the data and you can say that the sample proportion is our best guess for the population proportion. It's not biased. Any questions on that so far? Okay, and then part 2 is a little harder, and that is the standard deviation. Now, the standard deviation of the sampling distribution is not going to be the same as the population standard deviation, because it doesn't even make any sense, because there isn't a population standard deviation. It's a yes or no question, right? We're asking you, will you ever feel comfortable on this Boeing airplane? That's yes or no. We can't even talk about a standard deviation, but you can look at all possible sample proportions, and those are numbers. We could talk about the standard deviation for those numbers. And that's the standard deviation of the sampling distribution. Okay? So the standard deviation for the sampling distribution is, and now let's write it out, and because it's a bit messy, I need to use a pen for it. So the first thing is we're going to call it sigma. You're used to that for standard deviation. But it's a standard deviation of all possible sample proportions. Proportions, we use p, but if it's a sample, we put a little hat over it. And this is sigma sub p hat. That's, again, it's a standard deviation of all possible sample proportions with that sample size. And that is equal to, there's a big messy formula for this. It's the square root of p times 1 minus p divided by n, where n is a sample size, p is the population proportion. So any questions on this formula? Starting to look more like math, isn't it? Okay, any questions? What I'm not doing, and definitely not doing, is deriving these formulas. And by the way, we can also say the mean being the same as the population mean, we can say mu, that's mean, right? But the population mean of all possible sample means, so it's mu sub x bar is equal to mu, is the notation we use for that. So mu sub x bar is the mean of all possible sample means. Mu is the mean of the population. So they represent different ideas, and the central limit theorem says they're the same. Any questions on this so far? One of the things I will let you know is that this week, I mentioned we don't have any major projects, there's no big test, but the chapter itself can be really confusing. In fact, my guess is some of you are already confused. Okay, I don't see a lot of questions, but you can ask questions. Please ask questions if you have them. Any questions so far? Okay, let's take a look at what we had. So first thing is that if you remember, our sample size was 1756 in this Boeing survey. So what we can say is that our sigma, let's change the color since now we're doing an example. How about green? So for our case, sigma sub p hat is equal to the square root, and we're going to use 0.2, 1 in 5, as our best estimate for p, because that's all we got right now. 0.2 times 1 minus 0.2 is 0.8. all over the sample size, which was 1756. Okay, and I do not expect you to do this by hand. That would just be silly. But I do expect you to know how to use a calculator. So see if you can put it in. I'll put it in also. I'm actually just putting it into my Google URL bar, and it'll give it to me. 0.2 times 0.8 divided by 1756, all to the 0.5 power. And what'd you all get? Let's see if you get the same thing I got. Make sure you know how to use your calculator. And again, you should all have the same number because it's just plugging it in. So what you get when you put it in. And I always recommend you bring your calculators with you to these so that you can practice along and make sure you know how to use your calculator and you get the same thing that I get. Good, good. So Bailey and I agree. Hopefully you all agree also. 0.0095. All right, notice that's about 1%. Is that clear to everyone? All right, now we learned about the standard deviation. What that says is that taking samples of 1756, if we have a 1 in 5 chance of the person saying yes, in this case, yes, I'm afraid, I'll always be afraid of this Boeing airplane, then you're likely to not be off by more than 1%. Because that's what standard deviation tells you, is the majority of those samples are going to be off by less than 1%. And in fact, most of the samples, about 95% of the samples, will be off by no more than 2%. Because if you double that, you get around 2%. Any questions on that? Any questions? Okay, there's another piece of the central limit theorem that I want to tell you about. And it's an important one. Let me continue writing. And what it says is if NP, by the way, is the sample size times the proportion of yeses, and N times P is the number of yeses. Okay, it's your number of expected yeses is greater than, and in our class we're going to use 5. We need to have consistency. Sometimes you'll see them say greater than 10. And Q, but in our class it's always going to be 5. Greater than 5 also. Oh, sorry, and I better write it. I'm going to write it as Q and then I can explain what that means. Greater than 5 also. So P is a proportion of yeses. Q is a proportion of proportion of no's. So Q is 1 minus P. And so NP is the expected number of yeses, and Q is the expected number of no's. And if both of those are bigger than 5, then the sampling distribution is approximately normal. And that's a huge deal. Because what that says is that if you have a large sample size, large enough so you expect at least 5 yeses, or sorry, more than 5 yeses and more than 5 no's, then we can use our normal distribution and you can do all your calculations with the normal CDF and imp norm, which is nice because that's an easy one in the calculator. Any questions on how important this is? All right, I wanted to start out with this because this is one of the biggest mistakes students make, is not doing NP and NQ greater than 5. Because there's a part 2 of the central limit theorem with a different number. But I want you to know this one whenever it's a proportion. And today is the first day I'm really going to focus on this. And I'm going to focus every day for the rest of the class on this. Is the first thing you always do on any statistics problem from now on is you say, is this a yes-no question or is this a quantitative question? And if it's a yes-no question, then that means we're looking at N and P and N and Q. So it's proportion of yeses. And that means we're seeing if NP and NQ are greater than 5. Okay, right now, you probably don't even understand why would you be confused about that, because it's no big deal. Okay, in our case, let's take a look. It's actually not that hard. So in our case, we have NP is equal to 1756. That was our N, times P, which is 0.2. Okay, and that's about 350 or so. Any questions on that? Right, 351 if I do it in my head right. And I hope you all know that 351 is much bigger than 5. Similarly, NQ is going to be equal to 1756 times, so I better make this bigger. There we go. 1756 times 0.8. And that'll be 1405. If I did it in my head right. You don't have to do it in your head, by the way. Any questions on this? And 1405 definitely is bigger than 5. So what we can conclude is the sampling distribution is normal. So all probabilities you might be interested in, you can use the normal distribution. Any questions on that? Okay, now there is an assumption that you have to make, and this is what we talked about at the very beginning of class and also in your projects. Yeah, 1 minus P is Q, Charles. Good question, and that's just always going to be true for the rest of this class. We'll use Q for 1 minus P. We'll never use Q for anything else. It's kind of a standard letter in statistics. And P, on the other hand, is used for a few things, but for today, we're going to be using it as the proportion of successes. Or proportion of yes answers might be the better word, but sometimes you'll call that success even if it doesn't have to be good. Any questions so far? Okay, so the next thing is, now that we know all this, we could start doing things like saying, well, somebody said, well, maybe we're off by 5%. Maybe it's not 20%, maybe it's 25%. But we could actually compute that now, because we can now find what is the probability that it is, instead of 20%, let's suppose what's the probability that it's greater than 25%. Do you see? And let's do that. So probability, I'm right up here because I don't have a lot of space left, that x is greater than, I'm sorry, not x, but p is greater than 0.25. Maybe I'll p hat. In other words, if you're going to do a study at which 20% said yes, what's the probability that it's greater than 25%? Actually, the other way around, sorry. So if it were 25%, what's the probability that p hat would be greater than 20%? Maybe I should even write, let me change that, sorry. make it just right on this. That's what I really want. Let's do it one more time. So we want the probability that p hat is less than or equal to 20% given p equals 0.25. Any questions on this idea? Because that's what I asked at the very beginning is, how likely is it that maybe we're talking about 25% for the whole population? And I think, let me pop that in. P hat is the sample proportion. It's a good question. So P hat is a sample proportion. So Bailey, for example, thought that maybe we're off by 5%. So if we're off by 5%, then you might say, well, maybe P is 0.25. So you say, if P was 0.25, what would the probability be of getting a sample that's less than or equal to 0.2? And let's see if that's a big probability or a small probability. Any questions on that? Is that clear? All right. Well, we could do the same thing, but instead of this 0.2 and 0.8, we could do 0.25 and 0.75. So I'm going to do that. 0.25 and 0.75. I'm going to just stick it in my calculator. And I get 0.01. It's still about 1%, by the way. All right. Well, we have a big enough sample, so we can use the normal distribution. So now we can do and say we can use a normal distribution where our mean of the sampling distribution is 0.25. Our standard deviation for the sampling distribution was 0.01. And we want the probability that we're less than or equal to 0.2. So now we can go to our calculator. So I got to reshare. And that's easy. We know how to do that from the last chapter. We go second distribution. We do normal CDF. And our lower is negative bunch of 9s. Upper is 0.2. Mu is 0.25. And sigma was 0.01, because we calculated that. So let me ask, are there any questions about how I got these four numbers? Because we want to be less than or equal to 0.2. So that goes from negative infinity to 0.2, and you use negative 999. Okay, so then we just enter a couple times. And let me ask you, is the probability 2.87? What do y'all think? Definitely not. What is the probability? Yeah, it's not 2.87. It can't be. Probabilities can never be bigger than 1. So please never do that on the test. Whenever you're asked for a probability, never write a number bigger than 1. It can't ever be right. So notice this E. This E means move the decimal place 7 places to the left. So to do that, we're going to get 0, point, and then 1, 2, 3, 4, 5, 6. 6 zeros, and then the 287. And that is the probability that had it been 25%, that a sample with that sample size that was randomly taken would have a sample proportion 20% or less, or 0.2 or less. Any questions on that? Okay, any questions? And by the way, that's a really small probability. So looking, and this is the whole point. This is the whole point of this class. So now we can throw out the idea that 25% of all North American and Europeans are afraid, will never be okay with flying on that Boeing. Why is mu 25? Because what we wanted to do, and this comes, if you look up in the chat box at the top, I just decided I'd choose Bailey's answer because hers was the first to answer. And she thought we might be off by 5%. So if we're off by 5% and we said 20%, that makes it 25%. Does that make sense, Alex? So we're saying, had we been off by 5%, that means the population mean is 25%. Is that clear, Alex, or is that confusing still? So our sample proportion was 20%. If we were off by 5%, that would make it to be 25%. And now we're going to say that no, that is such a small probability that we're not off by 5%. Okay, it's very, very, very unlikely that that would happen. Okay, and that's the power of statistics. And notice that they only asked 1,756 out of the hundreds of millions of people. And as long as you do a good study, unbiased sample, this works. So we could say that this estimate with a very, very small percentage of the population for your sample is good enough and accurate. Any questions on that? Any questions on this idea? And again, this is kind of the whole purpose of the statistics class, is to be able to make those kind of arguments. Yeah, if you wanted to do 80%, then the number would be 0.8 instead of 0.25. Does that make sense, Bailey? How the normal CDF is working as max. So let me go back to what I was writing, and that comes from what I had just written. Let's go back to right there. Okay, so notice we want the probability that p hat is less than or equal to 0.2, because that's what we got. We got 0.2 in our sample, or they got 0.2 in their sample. So why would it be 0.25 and not 0.5? Because what you guessed is that you're off by 0.5. So if you're off by 0.5, then that would make it 0.25. If you really meant that you thought it really was 50%, then I would have used 0.5. But I thought you meant that you're off by, your error was 5%. That they underestimated by 5%. 0.28. I have no idea where the 0.28 is coming. 80%, actually 80%, if you're saying the error was 80%, then it's actually a little silly because that means you're off by, that would mean 100%. Because 20% plus 80% is not 28%, but 100%. So Bailey, that's why I didn't use that one. Yeah, so I particularly didn't want to use that one. Because 100% just gets weird. So any questions on this example? Okay, let me give you another example that's actually really important and really useful. In fact, I'm going to give you, it's related to this one, but only to me personally. So I will tell you that this was horrible for me. Okay, not as horrible for me as the passengers on that plane, by the way. I didn't know any of them. Any guess on why this was a really bad thing for me? That this survey was bad for me? Any thoughts? Nothing to do with statistics, by the way? Okay, no ideas? All right, let me tell you, because I own Boeing stock. Yeah, I own Boeing stock, and it sucks. So it went way down. So I lost thousands of dollars because of this. But that happens. I made money in other things. And by the way, I made about $40,000 in Boeing stock since I bought it. So I'm way up. I'm not complaining. Okay, but I lost like 5,000 because of that crash. Okay, so that's the reason why it matters to me, because I lost big money. Okay, and that's going to happen. So now I want to talk about something related to it. Okay, let me ask you, put in your chat box or say it. How many of you have ever played the stock market? Have ever bought stock? Right, say yes or no, I bought stock. Yes, no, I haven't.
No.
Okay. All right. A lot of you have, which is neat. That's a good thing usually, hopefully, if you did it well. So I want to talk about different stocks. So I want to go, because that's another big thing in the news today. What happened in the news today? Also very bad for me. Anyone know? Yeah, stock market went down. So I want to look at it. And let me share my desktop so we can take a look at some things. All right, so let's go to new share. And I talk about this in a long video, but it's so important, like, to your life, that I figure I should do it in both, because it really can make a big difference in your entire life. And nothing to do with your schooling. It's more for your investment life. And it's that one. Okay, so this, by the way, is the stock market. And you'll notice the Dow is down 473 points. Okay, in particular, the stock I'm looking at, by the way, I'll tell you, that I'm thinking about, I've been playing the market, as they say, is NVIDIA. Anyone ever heard of that? Okay, they're a artificial intelligence chip maker kind of stock in gaming. And believe it or not, they went way down today. They went down after hours. That's a good thing for me. They made a graphics card. Okay, that's a good thing for me. Why is that a good thing for me? Any thoughts? And the hint is I'm playing the market. It's a good thing because I don't own it right now. And I'm playing the market. I'm waiting to see when I want to own it. Do you see that? So I want to talk about two investment strategies. One investment strategy is to buy NVIDIA, okay? To buy the graphic card that Alex has, right? Okay, so I'm thinking about maybe buying NVIDIA. By the way, I've bought it twice already. Made a lot of money because I play the market. Here's another choice. One choice is to buy a single stock NVIDIA. The other choice is to buy, let's say, the Dow. Now, what is the Dow? Anyone know what the Dow is? And it's called an index fund, so a Dow index fund. Anyone know what the Dow is? Dow Jones. You might have heard of that. Nobody knows? No one's heard of it? I thought it was famous enough that you guys might know. Not seeing y'all type it in. Still not seeing it. Okay, so let me tell you what it is. Okay, isn't it 50 big companies? You're really close, Alex. Actually, it's not in tech. They're diversified companies. And in fact, you can type it in. What are the companies of the Dow? Look at that. I didn't have to type in the rest. Google just knows. Okay, so the Dow is 30. It's 30 large publicly owned companies based in the United States. Okay? So what is the difference between buying the single stock NVIDIA and buying an index fund, which kind of does a sample of 30 stocks instead of a single stock? Any thinking about the difference in those two investments in things like risk factor and how smart it is, all that kind of stuff? Okay, and it all has to do with, as you might guess, the central limit theorem. Yeah, you'll have less risk for the Dow. Now here's the question. How much less risk? And I'm going to make an assumption that the stocks are independent, which is a false assumption, but we're going to do it so that we can do statistics. True diversification is very hard and complicated. I can't go there, but we're going to pretend the Dow is diversified and independent. Okay, so let's go back to our notepad thing. And I'm going to erase what I had, and I'm going to talk about the central limit theorem instead of proportions, but for means. So notice that when you're talking about stocks, it's not a yes or no question. It's a quantitative question. It's how much did that stock rise? Is that clear? And the Dow is a sample of 30 stocks. So we have a central limit theorem instead of for proportions. We have a central limit theorem for means. Yeah, so when I say independent, it means they're not interconnected due to the real world. So if one goes up, it's not likely that the other one's going to go up because the first went up. That's kind of independent. We had a definition a while ago, but that definition is too hard to use for this particular example. It's more like knowing one went up doesn't tell you about the other. So it's not a very good assumption for the Dow. But so if you're going to truly diversify, you're going to want to do it internationally, and you're going to want to make sure you buy in very different things, like real estate versus oil versus technology versus all kinds of totally different things, which is hard to do, by the way, but can be done. So let me talk about the central limit theorem for means instead of proportions. I'm going to do this in red because it's that important. So central limit theorem for means. So that means you have quantitative data instead of the yes/no question. And what it says is it's the same idea about sampling distribution. We're going to think about all samples of, say, size 30, okay, of stocks, okay, that are independent and randomly selected. Okay, so, and we're going to look at the sampling distribution of all possible samples of a fixed sample size, N, has, and now let's write down what it has. So I need to do a pen because I have to use symbols and stuff. The mean, we're not going to talk about p hat anymore because we're not talking proportions. Now we're talking about mu sub x bar. So mu sub x bar is equal to mu. So what that says is that if you look at the mean of all possible sample means, that is the population mean. Very similar to the population proportion and the sample proportions. So what that says, again in words, is that the sample mean is an unbiased estimator, or the best guess, for the population mean. Any questions on that idea and those symbols? Okay, now comes the next one. This is a biggie. And that's sigma sub x bar sigma sub x bar is the standard deviation of all possible sample means. And that is equal to sigma divided by the square root of n. Now remember, in business, when you talk about the standard deviation, that's the risk, because that's how much up and down it goes. And if it goes down, that's bad. So if you have a high standard deviation, that means you have a higher chance of it going down a lot. Whereas if you have a low standard deviation, that means you have a small chance of going down a lot. Any questions on that? And up a lot, by the way, too. So notice the square root of n is in the denominator. And so was it, by the way, for proportions. So what that says is that the risk acts like the square root of the sample size. So that if you take the square root of 30, you get a number between 5 and 6, right? Square root of 25 is 5, square root of 36 is 6. So the square root of 30 is a number between 5 and 6. So that means that if you look at the Dow, for example, then the risk is 5 to 6 times lower than just investing in a single stock. Any questions on that idea? Any questions? But your chance of making it rich is also smaller, right? You're more likely to just kind of get that 8 or 9% that is the average change in the stock market. Okay, so you're likely to get pretty close to that. Whereas if you invest in a single stock, you might lose a bunch of money or you might gain a whole bunch of money. Okay, so there's a much bigger risk on both sides. Any questions on this? Okay, then there's the next part. What was the next part for proportions? Do you remember? What did it talk about? The central limit theorem for proportions. Any thoughts? Do you remember? I already erased it, but it was there once. So what was the last part when we talked about proportions that was important? It's actually even more important for means. All right, there's a bunch of you. Don't all jump in at once, but at least one of you can tell me. No thoughts? Give me another couple seconds. I was hoping you remember a little bit. Okay, so the last part was saying that if your sample size was large enough, in particular NP and NQ bigger than 5, you had a normal distribution. So it's similar to this, but different numbers. So let me give you the central limit theorem's last piece. And it's actually 2 parts. So if the population distribution is normal, then so is the sampling distribution. Okay, so if you started out with a normal distribution for the population, then the sampling distribution will always be normal, no matter what the sample size, even if the sample size is 3. Okay? But we have more than that. If n is greater than 30, then the sampling distribution will be approximately normal. Okay, so what that says is that if you have a large enough sample, then you know you have a normal distribution for the sampling distribution. And if we want any probabilities, we can use normal CDF. Any questions on that? Notice, by the way, the Dow doesn't work. Why doesn't the Dow work? Yeah, it is 30, and 30 is not bigger than 30. In our class, we're going to use 30 as our cutoff point. Okay, occasionally you'll see it at 25. There's nothing special about the number 30, but we got to use something in our class. And 30 works pretty well. It gives you usually about a decimal place of accuracy. Okay, 100 gives you a couple decimal places. But the main thing is we're going to use 30. Where have you heard greater than 30 before? And the hint is I subliminally gave this to you. I wanted to make sure it was drilled in your brain. Where have you heard it? So where in this class did I tell you have to be bigger than 30? Don't tell me nobody remembers, since it was pretty recent. Yeah, Project 1. Project 1, I told you you had to have a sample size bigger than 30, because if you have a sample size bigger than 30, that means that we're going to be able to say that the sampling distribution is approximately normal. It does not mean the distribution of your sample is normal. So get that straight. The distribution of the sample for most of you were skewed. I think so far I've looked at 7 of the projects, and 6 of the 7 were skewed. Okay, and that was your sample, the distribution of the sample. The sampling distribution is more theoretical. It's all possible sample means distribution instead of the data in your sample. So that's confusing for a lot of people, but let me know if you have questions. I'll pause for a second to let you ask some questions. Okay, but if you happen to know the distribution normal for the population, which you usually don't, then you don't need a number bigger than 30. All right? This mu sub x bar is mu and sigma sub x bar is sigma over root n. That's always true, no matter what the distribution is. You don't need to know you have a normal distribution. You don't need a large sample. It's just true, as long as you have a sample. Any questions on that? Okay, so let me ask you something. Let's suppose that the population mean, I need a brush, sorry. Let's suppose the population mean for the stock market, for individual stocks, is 0.08. So in other words, on average, every year, you have an 8% gain. Okay, and that's pretty accurate, by the way. And let's suppose that the standard deviation is equal to 0.21. So what we can do is we can say, well, how risky is buying one stock versus buying 30? Any questions on that question? And when I say how risky it is what's the chance of losing money? Any questions on that? So just a note, what does it mean to lose money? So if we look at this and we draw our picture, and I'm going to assume we have a normal distribution so we can do some calculations. The mean is 0.08. And what does it mean that you lost money on the picture? Any thoughts? Yeah, it's negative, in particular if less than 0. So if we want the probability of losing money, we're talking about that area. Now, let's compare, and we're going to do it with a calculator. I better write a few things down. 0.08, 0.21, mu sigma. So with our calculator, we can actually calculate this probability for an individual stock and for, say, the Dow Jones. So let's go ahead and do that. Any questions on the question? So let's clear out. I'm going to go to second distribution. normal CDF. The low is still negative 99999 because losing money is to the left. Our upper is 0. Anything below 0, you lost money. Our mu is 0.08. And the standard deviation we said was 0.21. And let's paste. And let's figure it out. Okay, so there's a 35% chance that you'll lose money if you just invest in that one stock NVIDIA, for example. Any questions on that? Now let's compare that to the probability that we'll lose money if we invest in 30 independent randomly selected stocks. So I can go second distribution again. Let me go to normal CDF. So I'm still going to have the same lower and upper. Losing money means negative. Our mean is still going to be 0.08 because the central limit theorem says that mu sub x bar equals mu. Our standard deviation now is not going to be 0.21. It's going to be 0.21 divided by the square root of 30. Any questions on that? Because the central limit theorem says that sigma sub x bar is sigma over root n. And now I calculate that. And notice that instead of having a 35% chance of losing money, you have about a 2% chance of losing money. Huge difference. Okay, and you've probably heard, maybe you have, but probably have, that you heard the recommendation you should have a diversified portfolio or diversified investment. Who's heard of that before? Yeah, this is why. What you probably didn't know is how do you calculate how much better a diversified investment is in terms of risk than instead of a diversified investment, a single stock where you put all your money in one stock. Any questions on that? Okay, by the way, let's do something fun. Let's suppose the S&P, it's not the safest, so let me go to the S&P 500. Okay, and I'm making a big assumption that's not quite true, and that is that these are independent, but if they're independent, if you go to the S&P 500, let's change that 30 into a 500, because that's 500 stocks. Notice it's 0. So if you can somehow find 500 different investments that are independent of each other, randomly chosen, then you basically have no chance of losing money. And your average will still be 8%. Now tell me what bank you can go to and get 8% interest, because that also has no chance of losing money. Yeah, none. What do you think the banks do with your money? Any thoughts? Yeah, they do this. They get 8%, they give you 0.5%, and they make money. That's how they make profit. So if you're wondering, do we have any business majors in this group? This is big and, okay. All right, so we got Esther and Tia. So this is really important for the two of you, because this is definitely business. I figured I'd do a business example today, because it's a biggie. Okay, now the Boeing thing was more of a psychology example, because it's how people feel about it, and that's psychology. So I did a psychology example and a business example. But what the business says is that this is how banks make money, is they take your money that you stick in the bank, they invest it in a diversified portfolio. There's all kinds of regulations of how to, what it means to be diversified. And then they make a lot higher percent than they give you. Any questions on this? Okay. Now, if the whole market crashes, then all of a sudden you lose your independence, things go down, and that can happen. Then you've lost your diversification. And that happened in 2008, by the way. Okay, so if you're wondering what happened, that's what happened, is that they weren't independent and everything went down together instead of ups and downs randomly. Any questions on this idea? Are you starting to see the power of this class? Okay, this is a very powerful class. Okay, by the way, I still invest in individual stocks. That's because I do a mix of psychology and math. And I play on people's emotions. Sounds bad, but it's the whole country's emotions. Every time Trump tweets something and things go down, good time to buy, just to let you know, because then it comes back up. So for me, I do individual because I want a high standard deviation. Yeah, I want a high standard deviation because I am not looking on the loss side, I'm looking on the super gain side. And if you invest in a single stock, which is what I do, I have a much higher chance of getting a super gain, and especially if I can learn about it. But that's psychology with math, so it's harder. Just let you know that. You need to get good at it. So if you're going to do it, I recommend playing it without actually using any real money and seeing how you do. And if you can do well consistently, then put your real money in. Otherwise, it's high risk. Any questions on this example? Okay, I want to close with one last little formula. I don't know if I even need to do an example, but I want to just mention it because it's on this chapter. Okay, sometimes you're less interested in the average and more interested in the total. Okay, so an example of that is, let's do a business example again. Let's suppose you have a business, and I'll do a Tahoe example. Let's suppose that you have a sports shop, and are you more interested in the average amount of money people spend, or the total amount of money that your customers spent over the day? What do you think is more important to you? Okay, Esther says total, Charles says average. Esther's right. Okay, but Esther also said she was a business major, so that's more important. Total's still more important over the long run. All that matters is how much money you have in your cash register at the end of the day, not what average amount did people spend. Does that make sense, Charles? You care about how much money you made, and that's the total. Okay? In any business, whatever you're doing, it's always the total that matters. So let me go back and pop into my writing area. And I want to mention something. If I multiply this, if I multiply these numbers, so let's do that. I'm going to do that with a different color to show you I've multiplied. By n. That's the total, right? If we average, say, 5, and we had 100 people, then we made a total of $500, right? 5 times 100 is 500. Is that clear to everyone? So it turns out the central limit theorem for totals instead of for means is the same idea, except you don't use X bar. Use this guy, sigma X. Now, for those of you who remember your intermediate algebra, what does sigma mean? What's that capital sigma mean? Anyone remember? I'm getting a bunch of blanks. Maybe none of you remember. Yeah, good. Galaxy remembers. Galaxy S9. Yeah, so that's the sum. The sum is the total, right? So you put a sigma X instead of an X bar here too. Sigma X. Like that. Any questions on that? Now a little bit of math. Maybe I'll open it up, but this might be dangerous. Who remembers what n divided by the square root of n is? A little algebra. I'll let you put in the chat box. I'm going to write it slowly and see if you can beat me. So it's sigma, and then n over root n is, I don't see you all jumping in. N divided by root n is actually root n. and that's algebra. Okay, it's n to the 1 over n to the 1/2 is n to the 1 minus 1/2. 1 minus a half is a half, so it's n to the 1/2, which is root n. So that's the proof. Okay. Any questions on that? Okay, I want to mention something. And I want to mention some notation. I talked about it last week, and I want to talk about it this week too. And that is, if I ask you, what is the distribution? So maybe I better type that out because that's important. If the question is, what is the distribution? And if we're talking about means, then remember, means, sample means are x bars. So the first thing is you use the letter x bar. And then if you remember that we did last week, you make a tilde. Do you remember that? And then you go n for normal. And our example was 0.08. Comma, and then our sigma was 0.21 divided by the square root of 30. All right, so now I want you to promise me something. I don't know if you remember, I had you promise something on the orientation video too. So I want you to promise me that if I ask you what is the distribution for means, that you're going to remember to divide by the square root of the sample size. So write, I promise in your chat box. There's a reason I'm making you do this. I'm going to try it. I haven't tried this before. I'm going to try it, see if it works. Okay. Okay. Any guess on why I'm making you say I promise? Any guess? Okay, if you're not guessing, I'll tell you. It will be on the midterm, and it will be on the final exam. Yeah, not just important, there's a guarantee. So I'm seeing if that'll help you remember to do it. Okay? So if we're talking about means, that's the notation you write out. If we're talking about sums or totals, same idea, but now you write sigma x tilde n, and it won't be 0.08 anymore. It'll be 0.08 times 30. It won't be 0.21 over root 30. It'll be 0.21 times the square root of 30. So depending on what you're looking at, if you're looking at an individual, then it's just 0.28 comma 0.21. If you're looking at a, what's that one called? Total or sums? Kind of two words for the same thing. So basic English, that's the good news, Bailey. So either total or sum. So if we're looking at the sum, then it's sigma x tilde n, and then you write down the mean times the sample size, comma, the standard deviation times the square root of n. Any questions on these examples? Okay, and I will promise you, you're going to have to do that. The other thing you're going to have to do is the picture. Okay, and I will let you know that the picture, that's not something I can have you do on the computer homework because the computer is not good enough at reading a picture. I actually created, believe it or not, I created an app where you had to draw it and it graded your drawing. And It did pretty well, but some people had trouble with it. So I didn't put this on the homework. But I actually made an app that made you draw and actually graded on how accurate your drawing was. That was a lot of work to make that happen. If you've ever programmed, you can imagine how much work it is to read somebody's drawing. Okay, full AI stuff. Any questions at all on the central limit theorem? Any questions? Okay, what do I need to do right now? Hopefully you all know. What I'm about to do. Let's do it in black because we don't have much black. Yeah, secret word. So let's get our secret word. And the secret word for today is, where is it? There it is. Make that bigger. Is sampling, because the central limit is all about the sampling distribution. So we can see it. Uh-oh, what just happened? Oh no. Sorry, let's put it back in. Okay. Notice it's a big piece of the central limit theorem. Oh, you guessed it. Pretty good. Okay. I try to make it important, but not obvious, but maybe I made it too obvious because I don't want everyone to be able to guess what it is because I want you all to watch the video if you haven't. But the sampling comes up a lot. It's different than the sample. Sampling. Because it's a verb. You're sampling a bunch of things. So that's about all I have to say for chapter 6. We're only doing one chapter at a time now for the rest of the quarter. Just let you know that. That does not mean the quarter is easy. Each week is only going to have one chapter. What it means is the chapters are harder. So you'll notice this had a lot to it. It's not a lot of information, but I think it is, it's abstract, it's deep. And next week, we're going to be using the central limit theorem in a big, deep way, doing what's called confidence intervals. And then the week after, we'll use the central limit theorem more. And after that, we'll use the central limit more. Ah, Galaxy S9, you're Brenda. Hi, Brenda. Okay. All right, so if anyone has questions, this is a great time. I'm going to unshare so we can see each other. I'm wearing my favorite shirt. Any questions? And as always, if you don't have questions and you want to say goodnight, that's fine too. But if you have questions, I'll be happy to answer the question. So any questions? And you can talk, you just have to unmute yourself. Okay, good night, Esther. And good night, thank you, Juliana. Good night, Zach. Yeah, this week is a survey news. Look at my post. A recommendation is make sure you can answer your own post in a similar way that I answered mine. Okay, although don't answer it, just put it on paper. Don't submit it or anything. But if you can't answer it, that might be a problem. It's similar to what I did today. Does that make sense? So it's similar to what I did today where I did I looked at an article and it gave a sample size, so we were able to figure out what the sampling distribution was. So you should all be ready now to do the post.
Cool. Thank you.
All right, thank you. Brenda? Okay, any questions, Bailey or Charles or Jake? When you went to normal CDF, okay, so Charles, never PDF. So that's the first thing, is never PDF. Yeah, okay, so let's look at, yeah, so I wonder if this will work. I'm not sure. I think there's a way of changing the calculator settings. Let me go, is it File, Edit, View, Calculator Model. Let me try that one, see if that works. If I go to second distribution, normal CDF, enter. Nope, still does it. So this only has the newer one, sorry. So, but I can still do some stuff. -999, for example. Enter. 0.08, enter. Actually, that was mu, not sigma. Let's try one more time. Just 0. 0.08. Enter. There's a reason I'm showing this, by the way. 0.21, for example. Okay, so this makes it really big. Sorry about that. So your calculator is just going to say normal CDF with a parenthesis, and you just type in -9999. Then you put the comma. Comma, by the way, is right above the 7. And then you put the comma, 0, and then comma, 0.08, and then comma, 0.21. So it's low, high, mean, standard deviation. Yeah, low, high, mean, standard deviation is the order. Same order that I put it in with the menu. It just doesn't give you the hints with the older calculators. Older ones are quicker, actually. But you have to remember what to do. Okay, any other questions, Charles? Okay, you do have a good night. And for all of you who are watching this as an archived webinar, thanks for watching. Make sure you put the secret word in, all of you. And I'll see you next week.